My name is Shizongqin from Tsinghua University. Today I would like to present our registered report, NSFuzz, towards efficient and stateful network service fuzzing. So currently, network service runs on almost every online device, and the vulnerabilities in such programs may bring some more security threats, since attackers could launch remote exploits much easier than the local target. So it is vital to find the vulnerabilities in such security critical targets. And now fuzzing is one of the most popular vulnerability discovery techniques, especially the coverage guided gray box fuzzing that could achieve high efficiency and low false positive. However, the existing gray box fuzzers mainly aim at the stateless local applications. As for network service, traditional works mainly use the black box fuzzing to find bugs, and some tools such as the Bitfuzzer and BlueFuzz are still very popular today. And recently, some works have also tried to apply the gray box method to fuzz network service. And in addition, for stateful programs, some works try to build a state module or design some specific feedback mechanism to guide the fuzzing process. However, many works may still have some limitations in testing efficiency and state representation towards network service fuzzing. So in this work, we will try to address these problems. So we analyzed the features of the network service programs. Compared to the local applications, network service always involve multiple I/O interactions with the client. Besides, for some services based on the stateful protocols, they would have involved state transactions during the process of multiple interactions. And such features bring challenges to fuzz the network service. First, due to the stateful feature of network service, a fuzzer without state-aware may mislead the evolutionary direction of genetic mutation algorithms. And the AFLNET is the first state-aware gray box fuzzer. It uses the response code to represent the service state. However, the response code may not always be available in every protocol, and sometimes the response code can only provide a limited state indication. And secondly, due to the multiple I/O requirements, the fuzzer also needs to conduct multiple interactions to fuzz the service index. Thus, the control of the interaction is important to the fuzzing efficiency. Some recent works use a timer to control the interval of I/O interaction activity, and the delay of time waiting may lower the throughput to some degree. And in order to design an efficient network service fuzzer, we studied the implementation structure of network service. Here is a code snippet from an FTP service. And we found some features of the implementation may give us some useful insights. First, we found that many services contain an event loop structure to receive a request message and process it with response continuously. That is, perform multiple I/O interaction with the clients in such loop. Second, we found many services may use some specific variables to record the real-time service state directly. And then in addition, the value of such variables may influence the code range in some service. And the variables may be updated when the service process messages, which indicates the state transactions. So here we got some insights from the case study. For the service state representation, many network services always use some specific variables to represent their state directly, and such state variables may represent the state more accurately and reasonably. As for the testing efficiency question, network service also have some points to indicate the message processing status. For example, the beginning of the event loop denotes that the previous message has been handled, and such I/O synchronization point could give the fuzzer a timely feedback to enable more efficient I/O interaction. So it could speed up the fuzzing. So in this work, we designed an efficient and state-aware network service fuzzer NSFuzz. We used variable-based service state representation and an efficient network I/O synchronization mechanism to carry out the network fuzzing. So here is the overview design of NSFuzz. Firstly, it performs static analysis to identify the event loop and the state variables. And then it conducts compile time instrumentation to enable the target to realize the signal-based fast I/O synchronization and the variable-based service state tracing. And finally, NSFuzz then carry out the efficient state-aware network service fuzzing loop. Currently, NSFuzz uses static analysis to identify the event loop to locate the I/O synchronization points and extracts the state variables in the network service. It uses the backtrace when the service receives message to identify the event loop that contain network I/O while avoiding the loop nesting cases. And it also uses a series of heuristic routes to extract the state variables. And based on the result of the static analysis in the instrumentation part, on the one hand, NS would insert a signal rising function at the I/O synchronization points to send signal feedback to fuzzer after each message is handled. And on the other hand, NSFuzz would also insert a state tracing function at the store operation of each state variable to update a region of shared memory between the fuzzer and the service. Here we call it the shared state here. And the NSFuzz could just use the shared state to represent the service state. After completing the instrumentation, NSFuzz starts the fuzzing loop to test the instrumented target. This figure describes the I/O synchronization process between the fuzzer and the service under test. First, each time the fuzzer sends a message, it would wait for the signal feedback from the service. And when the target service receives the message, it would process it and update the shared state, then send a signal feedback to the fuzzer. And once the fuzzer receives the signal, it would collect the state representation based on the shared state, then prepares to send the next message. And as for the service state tracing, now we would demonstrate the process of shared state update and how the fuzzer collects the state, how to make the state collection. So each time the fuzzer receives the signal feedback, as we mentioned above, it would hash the shared state to collect state representation. And during the message processing, some state variable would be updated and leading to the change of the shared state. Usually, a network service may contain more than one state variable. Thus, a change in any state variable will change the hash of the host shared state, representing different service states. So in the next time, the fuzzer would continuously collect state representation to build a transaction sequence and finally infer a state module for the target. And then it could use this module to guide the fuzzing process. During the evaluation part, we performed several experiments to answer the following research questions. The first question is, could NSFuzz inference a relatively more accurate or reasonable state module based on the state variable during the fuzzing process? And the second question is, could NSFuzz achieve a higher fuzzing efficiency and the overall result than any existing approaches? Currently, we selected 7 targets from the network protocol fuzzing benchmark ProFuzzBench to evaluate NSFuzz. To make the comparison, we selected 2 gray box network fuzzers, AFLNET and STATEAFL, and another network-enabled version of AFL, which is AFLNWE, as the baseline to compare. As aforementioned, NSFuzz first uses static analysis to extract the event loop and the state variables. So this table shows the analyzed result, and NSFuzz could locate the event loop in these target services, covering different network protocols, and NSFuzz could also extract the state variables through the static analyze. During the fuzzing process, NSFuzz would infer a state module based on the combination of state variables, and some other solutions would also infer a state module for the service according to their representation method. This table shows the average number of vertices and edges of the state module inferred by different fuzzers in 12 hours. For some targets, NSFuzz could infer a more accurate and reasonable state module, as we can see. After the 12 hours fuzzing on let FTP service, NSFuzz could infer a state module with 5 vertices and 12 edges. And these vertices just cover all the 4 authority states of the let FTP service implementation. And as for the overall fuzzing efficiency question, this table shows the average throughput of various fuzzers toward each target service. We can see that the throughput of NSFuzz is better than other works. And for the code coverage, NSFuzz could achieve a higher code branch coverage on almost all targets in the 12 hours fuzzing. And this figure illustrates that NSFuzz could also explore the code branch faster than other works during the fuzzing process. And in addition, different fuzzers could trigger the same crashes on some targets. And the average time of NSFuzz to trigger the first crash is lower than any other fuzzers. Currently, NSFuzz still has some limitations. The main problem lies in the scalability. Firstly, NSFuzz could only support the C program target now due to the current static analyzer's capability. And secondly, some network service may use some event-driven libraries such as the lib event to build their programs. In this case, the event loop is implemented in the library instead of the service implementation. And so the message processing will happen in the callback handler, which violates our currently static analyze patterns. Certainly, there are still false positives in the static analyze, especially the result of extraction of state variables, which may bring some state explosion issues during the module inference. And we thought the fragility of the static analyzer mainly causes these limitations. The complex and various network service implementations need complicated ad hoc static analyze rules, making it difficult to design a general analyze scheme. To sum up, we analyzed the state representation and the testing efficiency challenges for network service fuzzing. Then we proposed the NSFuzz, a network service fuzzer combined with variable-based state representation and an efficient I/O synchronization. Finally, we preliminarily evaluated NSFuzz on Profuzz bench, and the results showed NSFuzz could infer a relatively accurate state module on some targets and achieve a higher fuzzing efficiency than some other existing solutions. And here, I would like to share some new progress we have made recently. Thanks to the feedback and the suggestions from the reviewers, they gave us a lot of helpful advice. So according to their suggestion, we have designed some user annotation APIs so that users could manually annotate the I/O synchronization points and the state variables in network services. These APIs template the current static analyze to improve the scalability of NSFuzz. And now we have successfully extended the NSFuzz to 12 targets in the Profuzz bench under the usage of such annotation APIs, which covering services in some other language such as C++ and other implementation patterns. And to study the impact of each optimization of NSFuzz, we are also conducting evaluation studies. We propose NSFuzz-V, which is NSFuzz with variable-based state representation enabled only to carry out the same experiment. And the preliminary results show that NSFuzz still could have some effect when we only use a better state representation scheme. And we will continue to conduct a more comprehensive evaluation on more targets. And that's all my talks. Thanks for the listening. And if you have any questions, we could discuss it here.